Hello everyone, welcome to Brain Blitz Audios. Today in this episode of VITEEE Questions with Solution, we are going to be looking at some questions of physics. So as you've all requested, we've moved on to solving questions of physics as well as chemistry. So in this chapter, we're going to look at questions which are related to laws of motion and work, energy, and power. So this topic is from grade 11 and it is very important in the syllabus for VITEEE 2021 for the subject physics. So we're going to be looking at some questions from previous years with respect to this particular topic. So let's begin. This question was asked in 2018. A machine gun has a mass of 5 kg. It fires 50-gram bullets at the rate of 30 bullets per minute at a speed of 400 meters per second. What force is required to keep the gun in position? Is it A, 10 newtons, B, 5 newtons, C, 15 newtons, D, 30 newtons? Well, for problems related to laws of motion as well as work, energy, and power, it's best if we take stock of our given information. So the mass of the gun, the machine gun, is 5 kilograms and it fires 50-gram bullets. So the mass of the gun, of the bullet, will be 50 grams. So each bullet has a mass of 50 grams, which is 15 to 10 raised to minus 3 kg. So in order to find out the force required, we're going to, use the time period as 1 minute. So the time period here is 1 minute. That means that the number of bullets we fire in that 1 minute will be 30. So here we have the rate of bullets fired, which is 30 bullets per minute. So we'll just find the force present in that 1 minute. So therefore, the total number of bullets are 30. And finally, we have the velocity of the bullets. So the velocity of the bullets is equal to 400 meters per second. 1 minute, again, we can take that as 60 seconds. So we know the mass of the gun, we know the mass of the bullet, we know the time period of firing, we know the number of bullets fired, we know the velocity of each bullet. So how do we find out what force is required to keep the gun in position? So over here, we're going to use Newton's second law of motion. Newton's second law of motion. So what does this law state? It states that the rate of change of momentum of an object is directly proportional to the applied force on that body. So that means the force applied on a bullet, on the number of bullets here, will be equal to delta P divided by delta T. So delta P is P final minus P initial divided by here time period is T. So since we're looking at the bullet here, so P final means mass of the bullet times velocity of the bullet minus mass of the bullet times the initial velocity, which we know to be 0 because the gun was at rest and the bullets were also at rest before firing, divided by the time t. So we can completely disregard this term, so we just have mb/vb divided by t to consider. So mb here is 50 into 10 raised to minus 3, and we need to find total mass here. So the total mass will be the mass of each bullet times 30, and then vb will be 400. So the velocity of the bullet is 400 meters per second, and the time here is given to be 60 seconds. So 50 into 10 raised to minus 3 is the same as 50 divided by 10 raised to 3. So that means 50 divided by 1000 into 30 times 4 gives you 120. I mean, let's put it as 30 times 40, so that makes things easier. So 30 times 400 divided by 60. So 0 cancels out here, 2 zeros cancels out here, and one more 0 that cancels out the 0 in 50. So what we basically have is 5 into 3 into 4 divided by 6. So 6 goes into 4 thrice. 2 goes into 6 thrice, 2 goes into 4 twice, 3 and 3 cancels each other out. So basically we have 5 times 2, which is equal to 10 Newton. So the force on the 30 bullets which get fired in a minute, that force is equal to 10 Newton. Now, according to Newton's third law, every action has an equal and opposite reaction. So that means the force of 10 newtons on the bullets will mean that a recoil force, a reaction force will act on the gun, and it is equal and opposite. So the force acting on gun will also be equal to 10 newtons. And since we have to keep the gun in position, so therefore if the recoil force is 10 Newton, then the applied external force has to be equal to 10 Newton. So therefore, in this question, the correct option is option A, 10 Newton. In this question, the basic thing is to apply Newton's second law of motion as well as Newton's third law of motion. So applying the second law of motion gives us the force on the bullets, and using the third law, we can conclude that the same force is the recoil force, and in order to keep the gun in position, we have to apply a force equal to the recoil force. So therefore, option A, 10 newtons, is the correct option for this question asked in 2018. We have another question here, also from 2018. The principle of conservation of linear momentum can be strictly applied during a collision between two particles, provided that the time of impact is A, extremely small, B, moderately small, C, extremely large, D, dependent on the particular case. So, in order to understand this question, we need to refresh ourselves with the requirements for an event to be called a collision. So a collision is an interaction between two or more particles where the following observations are noted. Number one, the total momentum or energy of particles gets conserved. So conservation of momentum takes place in a collision. That's requirement number one. Requirement number two, the motion of particles, so at least one particle, should change its motion abruptly. So if the motion of a particle is abruptly changed in an interaction between two particles, then that fulfills one requirement for collision. And the final requirement, an impulse acts on each colliding particle. So what exactly is an impulse? Well, an impulse is a large force acting for a relatively small time. So therefore, the correct option here would be option A, is extremely small. Because if the time of impact was moderately small, then it would not be considered a collision because there is no impulse. There is a force which acts on a particular time. So option B is incorrect. Option C, again, extremely large, is incorrect. Option D, depends on particular case, is incorrect, because this is one of the fundamental requirements for a collision. So an impulse has to act on the colliding particles. So therefore, a large force must act for an extremely small time. So the correct option is option A. The principle of conservation of linear momentum can be strictly applied during a collision between two particles, provided that the time of impact is extremely small. So this question was in fact a test on us understanding and applying the requirements for collision. So for collision, the total momentum has to be conserved, and therefore an impulse acts on each colliding particle. An impulse is a large force which acts for an extremely small period of time. So let's look at the next question. A running man has half the kinetic energy of that of a boy of half of his mass. The man speeds up by 1 meters per second to have same kinetic energy as that of the boy. We need to find out the original speed of the man. So here, the mass of man, let's take that as m kg. So therefore, the mass of the boy will be m divided by 2, because because it's in the question it says half the kinetic energy of a boy of half of its mass. So also according to the question, we have the relation that the kinetic energy of the running man is half that of the boy. So that means the kinetic energy of the man is half times the kinetic energy of the boy. So since we represent kinetic energy as half mv squared, we can apply that in this scenario. So kinetic energy of the man is half times capital M times v1 squared. So we take the velocity of man as v1 and velocity of boy as v2, and we do that in order to avoid confusions. So half mv1 squared equals half times half of m by 2 v2 squared. So we're not going to simplify anything out here. We'll just take this as equation 1. So in the second scenario, the man speeds up by 1 meters per second. So the velocity of man here will be v1 plus 1. And in this case, the kinetic energy of the man is equal to the kinetic energy of the boy. So that means half times m times v1 plus 1 squared will be equal to half times, not half times, because half into m by 2 times v2 squared. This is equation 2. So now what we're doing is we're going to compare both of these equations. So when we divide equation 1 by equation 2, so while we're doing that, we'll see an important relation. So half m v1 squared divided by half m v1 plus 1 squared will be equal to half times half m by 2 v2 squared divided by half m by 2 v2 squared. So half m cancels out on the left hand side. In the right hand side, half times m by 2 v2 squared gets cancelled. So therefore, the relation we have left is v1 squared divided by v1 plus 1 squared is equal to 1 divided by 2. So now, instead of, complicating matters by expanding the denominator, we take the square root. So therefore, v1 divided by v1 plus 1 gives you 1 by root 2. So therefore, under root of 2 times v1 equals v1 plus 1. So that means v1 times under root of 2 minus 1 gives you the number 1. So therefore, the value of v1 is 1 divided by under root of 2 minus 1 meters per second. So this is the correct value of the velocity of the man. So therefore, the original speed of man in this question will be option C. Option C is the correct option for this question. So all the other options are incorrect because they are not correct as per our calculation. So over here, the calculation is to compare the kinetic energy of the man and the boy, provided that we use the correct comparisons for his mass and then finding out the velocity as well. So option C is correct for this question, which was asked in 2018. So the next two questions are asked in 2017. So we have a 5,000 kilogram rocket which is set up for vertical firing. The exhaust speed is 800 meters per second. To give an initial upward acceleration of 20 meters per second squared, the amount of gas ejected per second to supply the needed thrust will be, take g equals 10 meters per second squared. So in this question, the mass of the rocket, the initial mass of the rocket is 5,000 kilograms. And then the velocity of that rocket when it gets fired is 800 meters per second. The acceleration which it gets initially, so we have an initial upward acceleration, and the value of that initial upward acceleration is 20 meters per second squared, and the value of g is 10 meters per second squared. So over here, we have the upward force, which is F, as equal to m times g plus a. So over here, initially when the rocket is starting to fire, there is no loss of mass, so force is equal to m times g, the acceleration, which is velocity by time. So here the acceleration is g plus a, so therefore you have 5,000 times 10 plus 20, so 30 times 5,000, which is 150,000 newtons. So there is an initial force of 150,000 newtons. But what we need to find out is the amount of gas ejected per second. So we need to revisit Newton's second law of motion. So Newton's second law of motion. So what it says, the rate of change of momentum is directly proportional to the applied force. And the constant here is 1, so therefore rate of change of momentum is equal to the applied force. So that means the value of force will be delta P divided by delta T. So the value of force can be expressed in two ways. You can write V times dm by dt or m times dv by dt, which we commonly know as F equals ma. So in the case of a rocket firing, that is this case, there is a change in mass, because as you fire the rocket into space, there is more gas used up, there's more fuel used up by the rocket. So therefore, the mass of the rocket continuously decreases. So therefore, mass changes. So that means in this case, F equals constant velocity times dm divided by dt. So dm by dt will be the value, that means the amount of gas ejected. So the amount of gas ejected can be taken as the value of dm by dt, which is force divided by velocity. So now we know the value of force, which is 150,000. So this is the initial force, divided by the velocity, which in this case is 800 meters per second. So we cancel out the two zeros. You get 1,500 divided by 8. So we need to find the closest multiple of 8 to 150. So when you do 18 times 8, 8 times 8 is 64. 1 times 8 is 8. 8 plus 6 is 14, 144. If you were to take the next value, it will be 152, which will be higher. So therefore, 18 times 8 gives you 144. So you get 6 as the result. So put the 0 down, you get 60. We need to find out the closest factor, this closest multiple to 60. It's 8 times 7, which is 56. So 60 minus 56 is 4. There is a remainder. So when you put in a point, you can add a 0. So you get 40. 8 times 5 gives you 40. So 40 minus 40 gives you 0. So therefore, the correct answer to the value of the amount of gas ejected is 187.5 kilograms every second. So dm by dt is 187.5 kilograms per second. So therefore, the correct answer to this question is option D, 187.5 kilograms per second. So in this case, we need to find out the initial force by using F equals ma, and then the amount of gas ejected by using the formula for force, F equals vdm by dt. So basically, both of them are correct with respect to Newton's second law. In the first case, the mass remains constant. In the second case, the mass progressively decreases, so therefore progressively changes, so therefore it is the mass that we are differentiating in this case. So this question was asked in 2017. Let's move on to the final question of this episode, again asked in 2017. A smooth sphere of mass capital M is moving with a velocity u, and it directly collides elastically with another sphere of mass small m, which is at rest. After collision, their final velocities are capital V and small v respectively. You need to find the value of small v in this case. So let's once again write down what we have. The mass of the first body is capital M, and that of the second body is small m. The initial velocity of capital M is u, and the initial velocity of small m is 0 because it's at rest. The final velocity of capital M is capital V, and the final velocity of small m is equal to small v. So, basically uppercase v and lowercase v respectively. So we need to find out the value of lowercase v with respect to mass and initial velocity. So, how do we solve this question? So, in order to solve this question, we will use the fact that these two objects collide elastically. In elastic collision, so by the way, I'm talking about in space elastic collision and not inelastic collision. That's a whole other concept. So in space elastic collision, the linear momentum and the kinetic energy of both objects is conserved. So therefore, there is a conservation of linear momentum as well as conservation of kinetic energy acting in this scenario. So therefore, first we're going to apply the conservation of linear momentum. Conservation of linear momentum. So basically it means that the initial momentum is equal to the final momentum. So the initial, so mass 1, so mass capital M has a velocity u, but the mass small m was at rest, so that is small m times 0. So initial velocity, that is the initial momentum, and in final momentum we have capital M times capital V plus small m times small v. I mean, uppercase M times uppercase V plus lowercase m times lowercase v. So this term here, it is basically non-existent because anything times 0 is 0. So you have uppercase m times lowercase u equals uppercase m times uppercase v plus lowercase m times lowercase v. So what we're going to do here is to get a relation for uppercase v. So uppercase m times uppercase v equals uppercase m times lowercase u minus lowercase m times lowercase v. So therefore we get the uppercase v, that is the velocity of mass uppercase m, as equal to uppercase m times uppercase u minus lowercase m times lowercase v divided by uppercase m. So this is the initial, this is the final velocity of mass uppercase m. Next, we apply the conservation of kinetic energy, which is KE for short. So that means the initial kinetic energy is equal to the final kinetic energy. So initially, the kinetic energy of the system will be half uppercase m times lowercase u squared plus half lowercase m times 0 squared, which is again 0. So the final kinetic energy will be half times uppercase m times uppercase v squared plus half times lowercase m times lowercase v squared. So this term gets cancelled. We can now eliminate half across all terms. Because it's present across all terms, we can eliminate half. So therefore, the relation now becomes uppercase m times lowercase u squared is equal to uppercase m times uppercase v squared plus lowercase m times lowercase v squared. So in this particular question, we need to find the value of lowercase v. So lowercase m times lowercase v squared is taken on one side, and on the other side, you will have uppercase m times lowercase u squared minus uppercase m times uppercase v squared. So remember, we had a relation for uppercase v. So now we'll apply that over here. So we have uppercase m times uppercase u squared minus uppercase m times, we put in the relation. So uppercase m times uppercase u, uppercase m times lowercase u minus lowercase m times lowercase v divided by uppercase m squared. So the m outside will cancel out with will cancel out the integer for uppercase m in the denominator here. So the relation now becomes uppercase m times lowercase u squared minus uppercase m times lowercase u minus lowercase m times lowercase v. This numerator gets squared, and the denominator is m without squared. So the m is raised to the power 1. So now what do we do? What we're going to do is we're going to eliminate this denominator. So therefore you get lowercase m times uppercase m into lowercase v squared as equal to uppercase m squared times u squared, lowercase u squared, minus uppercase m times u minus lowercase m times v, and these two terms get squared. So therefore the correct relation will be m squared u squared minus, and inside the bracket you expand it in the form of a square minus b squared, so you get m squared u squared plus lowercase m squared v squared, lowercase v squared, and then minus 2 uppercase m lowercase m u lowercase v. So basically in this case you will have m squared u squared and m squared u squared getting cancelled, and then since the sign outside the bracket is negative, you get 2 m lowercase m u lowercase v as equal to lowercase m uppercase m and lowercase v squared. We also have minus lowercase m squared lowercase v squared in the right hand side. So over here lowercase m is common, so we cancel that out. So uppercase m lowercase v squared is equal to 2 m u v minus m lowercase v squared. So again we have v as common, so one of the v's get cancelled out from both sides, so you get m lowercase v as equals 2m u minus lowercase m v. So we take minus mv to the left hand side, so you get m lowercase v plus lowercase m lowercase v equals 2m lowercase u. So lowercase v times m plus lowercase m equals 2 m and then u. So therefore the value of v here will be 2 mu divided by m plus lowercase m. So what we're going to do is we're going to take m common out from the denominator, so you get 2 mu divided by m times 1 plus lowercase m divided by m. So therefore the expression for lowercase v, that is velocity of the second body, will be 2u divided by 1 plus lowercase m by uppercase m. So this is the correct expression for lowercase v. So therefore, among the following options, the correct option is option C. So option C gives you the correct answer for this question, which was asked in 2017. So in this question, we basically had to use conservation of momentum and conservation of kinetic energy because of the fact that both these objects collide elastically. So using that, we found out the answer, which is the value of lowercase v in terms of an expression. So that concludes this episode of VITEEE Questions with Solutions. We hope you found this episode interesting and helpful. For more of our videos, you can always subscribe to our channel, which is Brain Blitz Audios. If you want to access more of the content that we have uploaded regarding VITEEE, then don't forget to hit the playlist link in the description box down below. If you want to, get our updates regarding the latest content, so you can hit the bell icon, which is again present below the video. So until the next webisode, take care, stay safe, and I'll see you next time.